Hello, in this video we're going to look at how we can plot a line graph, which is a graph that is very important for physics. The reason we use a line graph is it allows us to compare two sets of variables that are continuously changeable. This is an example that's in your notes on page 25. And in this case it's describing an experiment that you haven't done yet, but you might do it at some point in the future, where we have a circuit and we change the voltage, which is really how strong a battery is, for example. We change the voltage and we measure the amount of current flowing through the circuit. Don't worry that if you don't know what this means yet. This is just looking at a independent variable, something that we're deliberately changing, and dependent variables that we are measuring. As we've done in the past, we've taken multiple readings and we're going to take an average. So I'm going to fill in the results for these, and then we're going to have a look at how we can plot a graph comparing our voltage and our current. In maths, in year 8, you're not really allowed to use a calculator. However, in physics, you are allowed to use one if necessary. So I'm going to quickly go through and work out the averages here. Just to give you a little tip, if you're using a scientific calculator like this, one with an awful lot of buttons on it, you have to be careful how you're adding up. Let's look at this second example, the 0.21, the 0.20, and the 0.19. If you type in 0.21 plus 0.20 plus 0.19, divide by 3, I get an answer of 0.4733 and so on, which is clearly the wrong answer because our average should always be bigger than our smallest reading and smaller than the biggest reading. The reason this has caused a problem is I've added that plus that divided by 3, not adding them all up together and dividing by 3. So really what I need to do is go 0.21 plus 0.20 plus 0.19, then press equals to get 0.6, then divide that answer by 3 to get our 0.2. So just be careful with that. It's one of the common mistakes that's made if people are using a scientific calculator for the first time. The instructions for our graphs is complete the table to find the average results. We've done that. Plot a graph of the results. Draw the axis, work out suitable scales, plot the points, and draw a best fit line. Now, what does that mean? Firstly, whenever you're drawing a graph, please use a pencil, not a pen. You cannot easily fix mistakes with a pen. So I'm going to use a pencil. Now, we want to draw a graph comparing voltage and current. Now, normally what happens is whatever is going to be your independent variable, the thing that you're deliberately changing, that's going to go normally on our axis along the bottom. So a graph has two things called an axis. This is called the x-axis, and this is called the y-axis. And so I'm going to draw those lines in first. You won't be able to see my pencil very clearly, so I am going to use a pen in this case to make it easier to see. And I'll use a red pen, but you're to use a pencil. So these are the axes for the graph. This axis is called the x-axis. This is called the y-axis. Notice how this is spelled AXES. That's the plural of axis. So this x-axis is going to represent our voltage, which in this case is the thing that we're deliberately changing, our independent variable. So we need to label the axis. And the label should really be the same as what's in your table. So I've got the title of what it's measuring and the unit after a slash. So this side is going to be current / amps. current in amps. Then we need to work out a suitable scale. Whenever you have a graph and you're given an area of graph paper, you need to make sure that you're filling up that graph paper. So you shouldn't have all your numbers squashed in here. Here's my voltage. It goes up 0, 1, 2, 3, 4, 5. So I'm going to start off with 0. And I could go 1, 2, 3, 4, 5. But that would mean I'm only using this area of the graph and all this area would be wasted. And you'd lose a mark for that. We want to use as much space as possible. So I'm going to do each big square, each 2 centimeters, as 1, 2, 3, 4, 5. And I've used a whole, certainly more than half of the available space. So I'm going to write 1, 2, 3, 4, 5. And 6 would be there if we're using 6. It's very important whenever you're choosing a scale to have an even scale so that each gap is the same size. So that's a gap of 1, a gap of 1, a gap of 1, and so on. And you must go up in nice, neat numbers. I've got up in 1s here. That's a nice one. You could go up in 2s or 4s or 5s, but you should never go up in 3s. You should never have a graph going 0, 3, 6, 9 or 0, 7, 14, 21. You're only allowed to go up in multiples of 1 or 2, 4 or 5. You could go up in 10s or 100s if it's appropriate, or 0.1s, and we'll maybe see an example of something like that when we get to a current. Here we have to choose our scale for the y-axis, the current. And our smallest reading is 0.0, and our biggest reading is 1. Now I certainly shouldn't go 0, 1, because that would mean I'd only use this area and not use any of this. So I want to fill up my axis again. If I put that 0.0 there, if I went 0.2, 0.4, 0.6, 0.8, 1.0, that will be ideal. That's going to use up the majority of our axis. In this case, you can see I've gone up in multiples of 2. I could, if I wanted to, label these as 0.1, 0.3, 0.5, 0.7, and so on. I'm not going to draw those, just to keep everything neat. So we've drawn our axis. I've worked out suitable scales. Now we're going to plot the points. And whenever we plot the points, we don't just put them as a dot on our graph. We're going to plot them as a small neat dot with a small neat circle around them. You can plot them with a little x, but I'm going to prefer the dot with a circle. So let's see what we have. When we have 0 voltage, we have 0.0 current. So go to 0 voltage, 0.0 current, and have a dot with a circle. At 1 volt, we've got 0.2. 1, 0.2. At 2, 0.40. So go to 2 and go up to 0.40. Now these 3 points have all been exactly on these big grid lines, which makes it nice and easy. 3 goes to 0.61. Now where's that going to be? Let's use a pencil for the moment. This point is 0.60. Here you can see there's little 2mm squares. What are they going up in? That's 0.7. So 0.6, 0.7. If we're going up in 5 little squares, it means that this square will be 0.62. So if I was to plot my point there, that's 0.6. There's 0.62. I want 0.61, so it's going to be halfway in between those. Now, how accurate do you have to be? Right the way up to A level, the accepted standard for how accurate your marking is as long as you're within one small square, either way around your point, it'll be marked correct. So if you were a little bit higher, a little bit low, that would be correct. But if you're more than one square out, you'd lose a mark. For 4, 0.79. So we had 4, There's 0.7, 0.8, 0.79 is going to be half a little square below the 0.8. And then for 5, 1.00, 5, 1.00. So now I've plotted my points. Finally, we have to draw a best fit line. Now, what does this phrase best fit mean? A lot of graphs you've maybe done in the past would involve you joining the dots. So if I used a ruler, certainly these first 3 points are all in a nice straight line. This point is a little bit higher, so I'd have to zig the line up a little bit. And there I'd zig it back down to that point. And then zig it again to there. And I've drawn a line that goes through all my points. Never do that in physics. Unless you're specifically told to, you never join the dots with a line. You might in other subjects, but in physics, that's not acceptable. We need to draw a line of best fit. This is showing a pattern, and our results aren't perfect. That's why actually we draw the points as a dot with a circle. It shows there's a little bit of uncertainty in our measurements. You know, our measuring device might be rounding a bit. We might have had to round a bit to record those answers. We can see these points are almost in a straight line. They're not perfectly in a straight line. However, in an ideal world, they probably would be in a straight line. And so the line that we actually should draw, our best fit line, is a single straight line that does its best to go through all the points. So in this case, I'm lining my ruler up. I've got it so that this, and this point are all on the line. This is a little bit above it. This will be a little bit below it. But that's the line that we're going to draw. I'll draw that one in red so you can see it clearly. So I've got a single straight line that goes through all the points. This pencil line that I've drawn is wrong. You should never have that. Never join the dots. And this line is showing the trend that we're investigating. We can see that really at 3 volts, we would have expected 0.6 amps. We got a little bit higher. That might just be a little experimental variation. I can also extend my line a little bit further. So I could say that's be 5.5. I would expect 1.1. And the point of a graph means I can now work out what the current would be for any voltage. If I said, well, at 1.4, 1.4 would give me 0.28. What voltage would I need to get a current of 0.9? I would go to 0.9, go across, come down, it would be 4.5 volts. And so I can use a graph to interpolate and work out other results that aren't there. Let's have a look at a few other examples of graphs. This is a question from an old GCSE double word paper. And let's see what the skills are that we've learned and can we apply them here. In this case, this is a bit more complex than you need to know, but I'm being asked to complete the table by entering the values of v squared. Here's the values of v, and I want to find out what v squared is. So we're just asking to square this. You won't have to do this until you're a few years down the line. So 1 squared is 1. 3 squared, 9. 4 squared, 16. 5 squares, 25. And we're asked to plot a graph of f against v squared. What does that mean? We're given this graph paper. Whenever we're told f against v squared, that means f is on the y-axis and v squared is on the x-axis. So it's always y against x. And the grid that they've given us already has the f, the force axis, labelled in. Choose a suitable scale for the horizontal axis, the x-axis, and label it. Well, we're told it's f against v squared, so this is going to be v squared. And we have to put in our units, and the units are just exactly the same as what's on our results table. This is more complex than the one that you'd see at year 8, but it's meters squared per second squared. Don't worry about that, I'm just copying it straight from the table. Then we have to choose our scale. Our smallest reading is 1, and in fact they tell us that our graph needs to start at 0. Our largest goes up to 25, so we need to get from 0 up to 25. 1, 2, 3, 4, 5. I've got 5 big squares, 25. Each one's going to go up in 5s. So 0, 5, 10, 15, 20, 25. So that's our suitable scale and our label. Plot a graph of f against v squared. So now we plot our points. And the points that we're interested in are the f points and the v squared. So when f is 0.5, well, where's 0.5? I have to go, it's going to be there. And where's 1? Well, I've got 10 little squares here, which means each 2 squares is going to be 1. So it's 0, 1, 2, 3, 4, 5. So when the force is 0.5, v squared is 1. There's my point. The force is 2, v squared is 4. 2, and that's 4. There's 4 down there. 4.5 goes to 9. There's 4, there's 4.5. There's 10, there's 9. 8.0 goes to 16. There's 8, 15, 16. And 12.5, way up the top, goes to 25. So now I've got my 5 points plotted. Draw the best fit line. Well, all of these points actually happen to fall on a perfectly straight line. So we can draw that in. And there we go. We're not going to worry about the rest of these questions. You haven't covered that yet. That's GCSE stuff. But now I can use this graph to work out at any force what's v squared going to be. So I can go to 6, go across, and that's going to come out at 12. Or 11, go across, and that's going to come out at 21, 22. Let's have a look at another example. Here's a set of results looking at T, temperature in degrees Celsius, and R, which is something about resistance. You don't have to worry about that yet, but it's measured in ohms. And we want to plot a graph of R in ohms against temperature. Again, choose a scale for the horizontal axis and label it. Well, our horizontal axis is going to be in temperatures, degrees C. T / degrees C, so that is exactly the same as that. We need to go up from 100 to 500. Well, I'm starting at 0. I've got 1, 2, 3, 4, 5. I'm going to go up in hundreds. 100, 200, 300, 400, and 500. Plot the points in the grid. 100, we get to 100. 200 degrees goes to 125. That's 100, 150, that's 125. 300, 150. 400, 175. And 500, 200. So now I've got a straight line, but notice it doesn't go down through 0, 0 like the other graphs have. That went down through 0, 0. That point 0, 0 we call the origin. Or this previous graph. Again, even though we didn't plot a point at the origin, we could see that the graph would extend down through the origin. In this case it doesn't, but we can still draw our best fit line. In fact, the next question on that paper would be draw the best fit line. So I'm going to get my ruler and line it up so it does its best to go through all those points, and in fact there is a single straight line that goes through those points. And we'll draw it the whole way through. So it doesn't have to go through the origin, although it often does. It is possible even to get a graph where all the points show a curve, like that or like that, but you'll maybe see those at another time. So in summary, whenever we're plotting a graph, we need to label the axes and label them so that we're using as much of the graph paper as possible. So I wouldn't want to go 100, 200, 300, 400, 500 and get a little skinny graph, or even 100, 200, 300, 400, 500 and use less than half the paper. If you're using less than half the paper, you can double your scale and use as much as possible. So work out a scale, label our axis so it should say what we're measuring and the unit, same as r/ohms. It should look at the same as results table. Plot the points, a small circle, not a big circle, but a little dot on the point, a small circle. And then we plot in our best fit line. If your points are a bit more erratic, you do your best to get roughly the same number above and below the line, although it doesn't have to be. Sometimes people like to join the first and last point. I don't like recommending that because the last point might be wrong. The advantage of this is it allows us to identify if we've made any mistakes in our results. If you plotted a point and there was one that was way down there, you can see that you've probably made a mistake and you can go back and repeat that result. I hope that helps, and in your test you will have to draw a graph a bit like this. This is the one that's in your notes, where you had to label all the axes yourselves, work out all the scales yourselves, plot the points and draw the best fit line. And remember, don't join the dots.